This video lecture is meant to cover the information found in Unit Number 13, the Gas Laws, Objectives 6 and 7, which say that you will compare and contrast real and ideal gases, and you will use the ideal gas law to quantitatively predict temperature, pressure, or the number of moles or liters of a gas. We're going to start by talking about Avogadro's law, which tries to relate the number of moles, the number of particles of a gas, to the volume. In this law, pressure and temperature both need to stay constant, and here we can see a before and after picture. On the left side, you can see here that there are, if you were to count those particles, there are 10 particles. The pressure is at 1 atmosphere, and what we see over here is a valve with a tank of gas that we are now going to add. We're going to double the number of particles, and that's what you see over here. After we've allowed some gas to be introduced into the container, there are now double the number of particles, and the volume has doubled. The temperature and the pressure has stayed the same, so effectively what we have is, with an increase in the number of moles of a gas, the volume will also increase, assuming that temperature and pressure remain constant. This is a direct relationship, as we have seen, and if we were to graph this, the graph would be sloping up and to the right. N represents the number of moles, and V represents the volume. The inference we can make from this law is that if two gases that are at the same temperature and pressure also have the same volume, it stands to reason that they will also have the same number of moles, which really means they'll have the same number of particles. So in a gas, if you have this two samples of gas, doesn't matter if they're the same gas or different types of gases, if the two gases are at the same temperature and pressure and they have the same volume, they will also have the same number of particles. So there's this idea that there are ideal gases, and you're going to hear about this, and so to define it, it is a hypothetical gas whose molecules occupy negligible space and have no interactions with each other. All right, so if you have a gas in that situation, that gas is obeying, demonstrating the kinetic theory. And if they demonstrate the kinetic theory, if they occupy negligible space and have no interactions, that means that they will obey the gas laws exactly. So the question is, how can a regular gas, a real regular gas, behave like this ideal gas? Well, how you do this is you make the gas as gassy as possible. And what that means is to have the gas needs to be in a gas state. And the best way to ensure that the gas is in a gas state is that the particles need to be far apart from each other, and they need to be moving quickly, moving fast. So what conditions are necessary to keep the particles far apart? Well, if we were to allow the pressure to be at a very low pressure, that wouldn't force the particles to be close together, and so naturally they would just be far apart. What conditions are necessary to keep the gas moving fast? Well, in this situation, moving fast means increasing the kinetic energy, which means we need to have the gas at a high temperature. So gases, when they are at a low pressure and a high temperature, will behave as an ideal gas, which means they'll behave this way, with negligible space, have no interactions, and that they'll obey the gas laws exactly. Now, if you were to bring the gas to a high pressure and a low temperature, gases would behave less ideally. In fact, if you bring the pressure too high and the temperature too cold, then you will actually turn that gas into a liquid. And in that case, of course, it's no longer behaving as an ideal gas at all because it's a liquid. So, bottom line, ideal gases behave ideally when the pressure is low and the temperature is high. Well, what we're going to do now is we are going to see the quantitative relationship between pressure, temperature, and volume when the conditions don't change. In the combined gas law, you had a sample of a gas that was at some initial conditions and was brought to some new conditions of pressure, temperature, and volume. You will use today's, the gas law you're going to learn about today. It's called the ideal gas law. When you know the number of moles of the gas. Okay, so for this particular equation, it's called the ideal gas law, and it is P times V is equal to N times R times T. And I suppose we should have the name written down here as the ideal gas law. Now you already know pressure is, P is pressure. We're going to use pressure in the units of ATM for this mathematical formula. Volume is V, which we're going to be measuring in liters. Temperature is T, which we're going to measure in Kelvin. Now in the combined gas law, it didn't really matter which units you used so long as they matched on either side of the equation. For this ideal gas law, you must use these units of atmospheres, liters, and Kelvin. And you'll see why in just a moment. We're introducing a new variable in here, and that's the number of moles. The abbreviation for moles is, of course, MOL. Now, R is what we call universal gas constant, and this is the reason it's a constant, it's a number, it's 0.0821, and the unit is atmospheres times liters divided by moles times Kelvin. Now, these are not things you're substituting in. These are the units. This is a derived unit. There are 4 units in this constant. Well, if there are 4 units in this constant, that means these other 4 variables have to have units that match those 4. So if I give you a pressure that's not in atmospheres, you will have to convert it to atmospheres so that it will match this atmospheres in this unit. So watch out for those as we go through these problems. First thing you're going to do is practice manipulating the equation, starting with PV equals nRT. If you solve for P, or solve for N, or solve for V, it depends on what the problem is asking for. If it's asking you to solve for pressure, solve the equation first for P, then plug your numbers in. So of course, to solve for P, if you're starting with PV equals nRT, to get P all by itself, you have to divide both sides of the equation by V, so this becomes P equals nRT over V. Then you can plug your numbers in for the particular problem. Solving for N, if you want N all by itself, you will have to divide both sides of the equation by RT. So N will end up being PV over RT. If you're solving for volume, to get V all by itself, you will have to divide both sides by pressure. So you get V is equal to nRT over P. All right, and so on this goes. If you were to do this, to solve this for temperature, to get temperature all by itself, you would have to divide both sides of the equation by nR, and so the equation rewrites to PV over nR. I am going to expect that on the test that you will be able to manipulate the equation first and show me the manipulated equation before you substitute any numbers in. Let's go through a couple of examples. First example here is you have a volume. What is the volume occupied by 0.355 moles of nitrogen gas at STP? So first, knowing that we are solving for volume, because it's asking for the volume, I would start with the equation solved for V, which is nRT over P. And then from there, I would start substituting in my moles, my universal gas constant R, my temperature, and my pressure. Moles are given to us at 0.355 mole. The universal gas constant is 0.0821 atmospheres times liters over moles times Kelvin. Temperature is given to us in these 3 letters: standard, temperature, and pressure. Standard temperature in Kelvin, remember we want to be in Kelvin, is 273 Kelvin. Dividing by pressure, standard pressure, STP, standard pressure in atmospheres is 1.000 atmospheres. So if we take a close look here, we'll see that moles cancel. We'll see that atmospheres cancel. And we will see that Kelvin cancels, leaving us with liters. When you plug this into your calculator properly, you will come out with a number that is 7.9567215 liters. Obviously, this number needs to be rounded. Our measurement, the original measurement that we used to start with, was 0.355, which is 3 sig figs, which we will use as our guide to round this number to 7.96 liters. All right, in the second problem, we have a 35.0 liter tank containing 7.00 moles of compressed air. If the pressure inside the tank is 4.93 atmospheres, what is the temperature of the compressed gas? So we're solving for temperature in this problem, so you would start with the manipulated equation T equals PV over NR. The pressure is given to us at 4.93 atmospheres. The volume is given to us as 35.0 liters. N is given to us as 7.00 moles. And the gas constant is a given 0.0821 atmospheres, liters over moles, Kelvin. If we take a look, liters will cancel, moles will cancel, and atmospheres cancel, leaving us with a temperature unit of Kelvin. And if you plug this number into your calculator, and I want you to try this, some students get wrong answers when there are two numbers in the denominator. Make sure you are dividing by the product of 7 times 0.0821. I want you to make sure you're trying this in your own calculator to verify that you get the same answer I do. The calculator spits out this number, 300.243605 Kelvin. All of our measurements in the original problem had 3 sig figs, so we would want to leave this to 3 sig figs, which would round to 300 point to indicate that we want to keep all 3 of those digits significant. So that is our final answer for this second problem. Number 3, how many moles of helium does a 25.0 liter balloon contain at 101.3 kPa and 24 degrees Celsius? So how many moles? That's N. Starting with the reworked equation, N equals PV over RT. We want to substitute in our variables, being careful to notice that we have units that don't match the universal gas constant units. So let's make sure we put in the correct numbers first. The pressure is given to us at 101.3 kPa. You'll recognize that to be standard pressure, which is equal to 1.000 atmospheres. So that was an easy conversion to think about. Now 24 degrees Celsius, that's Celsius. We need to make sure we add, if you add 273 and 24 to get your Kelvin, you will see that this is 297 Kelvin. Okay, so we want to make sure we use that temperature. So going back to our equation, the pressure is 1.000 atmospheres times the volume of 25.0 liters divided by the gas constant, 0.0821 atmospheres, liters over moles, Kelvin, times the temperature of 297 K. Watching the units cancel, atmospheres cancel, liters cancel, and Kelvin cancel, leaving us with the unit of moles. If you plug this into your calculator correctly, you will get the answer 1.02527508 moles. All of the numbers in our original problem, let's see, we had to round this down to 2 significant figures. Actually 3 significant figures, because Kelvin was the number that we actually used in our problem. So 3 is our fewest significant figures that are plugged in. So we would round this to 3 sig figs. So this becomes 1.03 moles. In our last problem, well, that was a little interesting typo. All right, in our last problem, we are going to calculate the pressure in a 212 liter tank containing 23.3 kilograms of argon gas at 25 degrees Celsius. So in this case, we're solving for pressure. The manipulated equation is P equals nRT over V. Now, here's a couple things we're going to have to do as an aside. We don't have moles, we have a mass. Okay? We don't have Kelvin temperature, we have Celsius temperature. So that's the easiest one to start with. Celsius temperature, you add 273. 273 plus 25 is 298 Kelvin. So there's our temperature. Now converting this mass, I'm going to do this problem down here. 23.3 kilograms. First we need to get it into grams before we can convert it to moles. 1 kilogram is 1,000 grams. Right? So if we leave the problem there, our answer will be in grams, but then we have to convert this into moles. And so from the periodic table, 1 mole of argon weighs 39.9 grams. If we leave the problem there, we will have our answer in moles. So 23.3 times 1,000, take that answer, divide by 39.9, and we have 584 moles. So we're going to use 584 moles as our N. R is 0.0821 atmospheres, liters over moles, Kelvin. Temperature is 298 Kelvin, all divided by the volume of 212 liters. If we take a look and see what cancels, moles will cancel, Kelvin will cancel, and liters will cancel, leaving us with a unit of atmospheres. If you plug these numbers into your calculator correctly, you will get the answer 67.3963547 atmospheres. We're rounding to 3 sig figs, and so that would give us 67.4 atmospheres as our final pressure. All right, you've now seen 4 examples for the ideal gas law. We'll be reconvening back in the classroom where you will get a chance to practice this equation together with me. All right, we'll see you in the classroom.